previous session, we have been discussing about data visualization and its importance, and we have ended that session with a question. So how do we decide if a visualization is good or bad? We have also seen a few examples of how a visualization can be really bad. So when we speak whether a visualization is good or bad, here we are talking about how the visualization is helping us in understanding the underlying data. So if the visualization is making it easy for us to understand the underlying data and to get insights from the data, then we call such visualizations as good. And if they are misleading or not representing the data properly, then they are the bad visualizations. Now, how do we decide if something is very good or something is bad? So we have principles of data visualization which are given by Edward Tuftes. Now he is a pioneer in this field of data visualization. So he has given out these 4 fundamental principles. Now there are so many other principles and aspects which we look into during data visualization, but let's cover these 4 principles in today's session with examples. Now they are maximizing the data ink ratio, minimizing the lie factor, minimizing chart junk, using proper scales, and clear labeling. Now let's look at them one by one. So to begin with, what is maximizing the data ink ratio? So if you look at this graphs, you can understand it with this example. Now data ink ratio is, you can see the formula. So it is data ink by the total ink used in the graph. Now this comes from a context where when you plot a graph, you might have a printer and you might actually print it. So then when you actually print this visualization, there is some ink that is used in order to create this visualization, right? So it comes from that context, the data ink ratio. But now you can think of it as the amount of ink that is used in the visualization. So you might not actually print it, but still when you look at it, you'll understand the amount of ink that is needed in case if you have to print it, right? So here, then what is data ink? Now data ink refers to the ink that is actually used to represent the data. So, and what is the total ink? Then the ink that is used, which is not essentially representing the data, but which is also adding some additional effects to the data. Now these additional effects can be something like some, you can see in the below example. So on the right side, you can see that the data, the corresponding data is represented in a nice graph. The same data on the left side, you can see we have made some 3D looking bars for the bar chart. And then there are these shadows which are falling behind each of these bars. Now these are the additional effects that we are creating, and the extra ink that we use in order to create these additional effects is not exactly representing the data, but it is the additional ink. So that is where this ratio comes from. So the data ink to the total ink used in the graph should be maximized. So that is what we have to do when we say maximize the data ink ratio. Now how do we maximize this? So maximizing this is nothing but minimizing the rest of these additional effects, which can be these shadow effects or some fancy kind of visualization, some 3D visualization where we don't actually need a 3D visualization. So for the data in the below example, you can clearly see that we don't really need a 3D visualization with all those shadows and all such things. Rather, we can simply put it as shown on the right side of the slide. So this is a very good example of how we can maximize the data ink ratio, and this is one of the first principles that is given by Edward Tufte. So we should always try to maximize the data ink ratio in order to create good visualizations. Now let's look at another example where the data ink ratio can be maximized. So you can see on the left side, we have a particular visualization where we have the number of orders per each category. So we have 3 different categories. So one is office supplies, the second is furniture, and the third is technology. And we have the different number of orders in each of these categories. and there is a visualization. Now the left, even though the visualization on the left side is representing the data accurately and all, but still we can maximize the data ink ratio in that particular visualization by removing all these unnecessary images and other kinds of text and all the effects, the gradient effects and things like that. And on the right side you can see a very simple visualization of the same data which has a high data ink ratio, right? Now this is the first principle, which is to maximize the data ink ratio. Now we will go into the next one, which is the minimizing life factor. Now what do we mean when we say minimizing life factor? So in some of the visualizations, as we discussed before, so the visualization might misrepresent the data. That means it might not show the data accurately, rather it might lead to some wrong conclusions about the data. So that is when we say that there is some life factor in the visualization. So now the second principle is to minimize this, minimize the life factor. So let's look at it with some examples. So this is one of the example. On the left graph, if you just look at the left graph, so just forget about the right side one, or just look at the left graph for a moment, and on the first glance, what is the impression that you get? So you can see that the graph is titled interest rates, and from 2008 to 2012 you can see there is an exponential growth in the interest rate. So that is the first impression that we get when we look at that graph. But is that true? No. So if you look at the y-axis on the first graph, on the graph which is on the left side, you can see that the numbers are 3.14, 3.142, 3.144. So that means the interest rates are not really changing much. A change from 3.14 to 3.142 is a very small change. It's a change of 0.002%. Now that is not a very huge increase in the interest rate, but the graph on the left side, the visualization gives us an impression that the interest rates are increasing exponentially over a period of time. On the right side, whereas on the right side you can see the appropriate representation for the same data. Now the data is the same, just the visualization, the way we are visualizing the data has changed. On the right side you can see, if you look at this visualization, you feel that the interest rates are more or less the same, right? Now that is a little more accurate visualization, which is giving the right kind of insight from the data about the interest rates, the data about the interest rates. So this is on the left graph, we can say that there is some life factor in that visualization. So we have to minimize such life factors because the underlying data is not properly communicated. So the data is, it is true that they are not changing the data is the same, but the way they are visualizing the data, it is creating a false image about the data and the insights from the data. So that is when we call there is this life factor in the data. Now going to further examples, now if you look at the left visualization, you can see that you have a credit score of 634 and it doesn't feel like you have really good credit score. It just feels like you are doing okay. So it feels like you have less than 75% of what is normal, right? But if you look at it carefully, so it is 634 out of 700. So on the right side you can see the same visualization. So it is 634 out of 700. So the 700 is also highlighted equally. And then you can see that the filling of the circle is more than 75%, which is more accurate representation because 634 out of 700 will definitely be more than 75%, right? So even though it is the same data, so the right side visualization is giving a more accurate representation of the data, right? So this is another example where there can be some life factor in the visualization. So even though they are not changing the data, but just the visualization is giving a wrong impression about the data. So, and few other examples, you can see that this is some news channel which is representing the COVID-19 cases in the US. And again, you can see the y-axis. So the y-axis that they are using is very wrong. So it's 0, 5, 20, 25, and it suddenly goes to 65K, which creates an overall wrong impression about how the cases are increasing in the US, right? So on the right side, you can see that the cases or the y-axis is scaled appropriately, like the differences between each of the each of the thing on the y-axis. So the 10K, 20K, 30K, 40K. So each of it, the difference between each of it is the same, right? Whereas on the left image or the left visualization, the difference is not the same. From 0 to 5, it's just 5. And from 5 to 20, the difference is 15. And from 20 to 35, the difference is 15. So the differences are not the same. Whereas on the right side, the differences are same, which will give an accurate representation of the data. So you can see that the growth is very exponential in that particular period of time. Whereas if you look at the same data in the visualization on the left side, it feels that it is growing, but it doesn't feel like the growth is exponential. It just feels like, okay, it is growing a little bit more than linear or something like that. So in this way, with the same data, we can create visualizations which can induce this life factor. So that should be minimized. The life factor, sometimes maybe people use it wantedly to create these life factors. So that is with their personal agenda. Then we should be very careful when we are looking at all of such visualizations in our day-to-day life. So we have to make sure that we are interpreting the data in the right way. We should not fall for these traps where there is life factor in the visualization. And when we are creating by mistakes, we might do some mistake and we might not realize, it might not be intentional some of the time, but that might lead to some life factor in the visualization. So we should make sure that we are not creating such life factors in the visualizations. So that is what we mean when we say minimize life factor. And another very interesting example, now an organization or some group wants to portray how a particular law on the guns. So this law is about some guns, and they have introduced this law, and they want to see the effect of this particular law on the gun deaths in a state of Florida in the United States. When you look at the graph on the left side, you get a feeling that you can see there. So in the first glance, you get a feeling that after 2005, when the law is enacted, the gun deaths in Florida has decreased. But that's not the case. If you look at it carefully, they tried to outsmart the users, probably because this is not a traditional way in which we draw any graph like this, because the 0 is at the top, the 200, 400, 600, 800, the y-axis is inverted. Now that gives a wrong impression about the data. Whereas you can see the same graph on the right side, which is created in a right way, in a proper way, you can see that the y-axis at the bottom it is 0 and it is increasing 200, 400. Now this gives a clear picture that after 2005, at that particular point, so there is an increase after that particular law, there is an increase in the gun deaths in the state of Florida. Now this is another example where there can be life factor in the graphs. Now they might try to make it a little fancier on the left side graph, or even they might just want to make a feeling in the users or whoever is viewing the graph that the gun deaths are actually decreasing. So we don't know their intentions exactly, but that particular graph is creating a lie factor and it is communicating a lie from the underlying data. So it's not projecting the data as it is. It is not helping us understand the data in an easier way. Rather, it is creating some wrong impression about the data, which is a lie factor. And another example is, this is a case where we add more dimensions when it is not actually needed. So in order to represent the increase in the price of petrol, so we can simply use the simple bar charts that we just looked at some of the examples. But rather what they try to do is they try to create this fancy visualization, the 3D visualization. On the left side you can see they are using these barrels. So maybe the barrel will indicate the price of a barrel or something like that, but still it is giving a wrong impression, because you can see that the sizes of the barrels, the increase in the size of the barrel is not proportional to the increase in the size of the actual prices. So you can see in the 1978, so the $12.7, and in the 1979 it is $13.34. So the increase in that price is just $0.64, but if you see the barrel size, it feels as if it has increased a lot. This happens because when you are using these extra dimensions, the increase in the dimension gives a feeling that even though if you increase the height by a little, the overall increase in the volume will be a huge, so it feels as if it has grown quite a lot. Now it's another similar example on the right side. Now this is the example of data where they have the family doctors, the number of family doctors are decreasing year after year. Now that is what they want to communicate from this visualization. You can see in the 1964 it is 27%, in the 1990 it is 12%, but using this kind of a 3D image doesn't accurately represent the change in the percentage of the family doctors. Rather, it creates a kind of a lie factor. So you can see on the top, the lie factor is, in this context, the lie factor is the size of the effect in the graph by the size of the effect in the actual data. That means the changes in the actual data are not proportionally represented in the graphs. Rather, the size effects in the graphs are very huge compared to the changes in the size effects in the actual data. So that is when we see the lie factor. So this should be minimized as much as possible. And in most of the times this happens when we use these extra dimensions which are not actually necessary. So if you reduce these extra dimensions and if you just stick to the 2 dimensions whenever it is sufficient, then these kind of lie factors can be minimized. Now this is the second most important aspect or most important principle, that is minimizing the lie factor. Now let's go to the third one. Before going to the third one, I just want to mention that most of these principles that we are discussing are interrelated. Now they are not just simply quite different and independent on their own, rather they are mostly interlinked. Now if we follow one of the principles, most of the times it might happen that we are also following the rest of the principles automatically. Now you need not look at them independently, rather mostly they are interlinked, but there are some subtle differences and the way we look at it, so that just changes in most of the times. So having said that, the next important principle is reducing chart junk. Now as the name says, we should try to avoid the junk in the chart. Now what is this junk in the chart? So there can be different kinds of junk in the chart. So one of the junk that we discussed is the unnecessary extra dimensionality. Now when we really need to represent something in a 3 dimension to make it understand more clearly, then we have to use it. But we don't have to use these 3-dimensional representations unnecessarily. Now that is kind of a chart junk, which also creates lie factor in some of the cases, and which also decreases the data ink ratio. So in order to increase the data ink ratio, we have to reduce these extra dimensions, so that we have also seen in the example. So that is the extra junk. Now another junk is using uninformative coloring. Now sometimes using different colors might give a really good visualization, might make it more insightful and more meaningful, but sometimes if you just use the colors randomly, like without even worrying about what they are, if you just keep on using different colors, then it doesn't make the chart any meaningful and any useful. Rather, it just makes it more confusing. Now even though the colors don't mean anything in specific, if you just use them randomly, now they might give some false impression about the data too. So we should avoid such kind of chart junk. Now another thing is not not using the excessive grids and decoration. So we should not use these excessive grids, excessive kind of decoration, some fancy visualization, some fancy images. So we should try to avoid them as much as possible. And even in avoiding them, we are essentially also maximizing the data ink ratio as well. And in some of the times, we might even minimize the life factor too in trying to do that. So these are some of the different kinds of chart junk which we have to avoid. And usually, instead of creating this fancy things in the visualization which leads to the chart junk, most of the times, what is an exciting graphic? An exciting graphic is not, a graphic is exciting not because of the kind of the fanciness that it has. Rather, a graphic is exciting when it actually tells the truth about the data, when it tells the truth about the data, and when it helps us in understanding the data in a more meaningful way and in a very easy way, instead of going through all the numbers and churning through the numbers and trying to make sense of the data. So that is when the graphic is actually exciting. So it's not the chart junk which makes the graphic exciting. So when I say graphic, it is nothing but some visualization of the data. Now let's just look at a few examples of this chart junk. Now this is when whoever is trying to do this, they try to represent the anatomy of a winning TED talk. That means they are trying to say different components which are essential to make a really good TED presentation or a TED talk. Now the visualization on the right, you can see that they try to make some three-dimensional pies and put them one behind the other, which is creating some, when you just look at it for the first time, it might look some fancy kind of thing, but it is not representing what the underlying data exactly is. So this is not helping us to understand the data. It is not serving the actual purpose. It might look fancy, but it is not serving the actual purpose of what a data visualization should do, right? So you can see on the left side, there are these numbers 49% and 23%, which is actually very small and which is not very clearly visible too. So this is an example of a really bad visualization with a lot of chart junk. And to give you an extreme example, you can look at this. So this is a visualization of COVID-19 death rates. So you can see the mortality rate of COVID-19 2020 in different countries. Now just pause the video and try to make a sense of this visualization. Now if you can't see it clearly, we will also give a link to this particular image in the description of this video. You can go through that and just try to make a sense of it. Then you will realize what chart junk is and how much junk this chart is. In order to represent some information, we are using a visualization. So why do we need these visualizations? When we have a lot of data and when it becomes very difficult in order to make sense out of this data or in order to understand some insights from the data, then we can't just churn through all of these numbers all the time in order to do that. Rather, when we create good visualizations from the data, it becomes a lot easier for us to understand, for us to get the insights, and also for us to communicate this data to the other people, right? So that is the purpose. But what this particular graph is doing, they are trying to visualize the underlying data. Now, it is completely defeating the purpose. It is going against it. So rather than getting some understanding of the data, we are getting more confused. So if you just look at this data, it keeps on confusing you. So, and it takes even more time. So if you just look at the plain tabular data, maybe you can understand what they are trying to say in a much shorter time, rather than looking at this particular fancy kind of visualization, where you might even take a lot longer to try to make sense of the underlying data and make sense of what they're trying to convey. It is even confusing too. So in this way, this particular chart junk, so we call such kind of things as chart junk. So this is a perfect example. Now I'm not trying to explain you what that is. You try to do it for yourself so that you can understand why we are saying it a chart junk, and you can maybe even think of how we can represent it in a better way. So this is one example. And now we can reduce this chart junk in multiple ways. Now again, this is another example of chart junk where we are using on the left side. You can see that this is not an extreme example like that of the previous one, but this is also an example of chart junk. You can see there are unnecessary grid lines and there is unnecessary background color. So rather on the right side, you can see that this is the same data which we are representing both on the visualization on the left and on the right. When you look at the right side visualization on the right, it looks a little more pleasant on the first site itself, and it uses less ink, of course. So we are maximizing the data ink ratio too by removing all the chart junk. So you can see that it is a more clean way of representing the same thing. So we can understand the comparisons, all these things very easily too. So when somebody asks you which is a good visualization, clearly you can say that the visualization on the right is good because it has less chart junk and is also maximizing the data ink ratio. Now this is the third principle, which is reducing the chart junk, and we have seen a few good examples of that too. Now going to the fourth principle, which is using proper scales and clear labeling. Now this also is very important, and some of the times not using these proper scales and labeling might also lead to the lie factor in the data. So these are closely related. So both the lie factor and the proper scales and clear labeling. Let's understand with examples. Now both the visualizations again represent the same underlying data, and the data is of a football team, and we are trying to represent the number of wins of that particular team across different years. So starting from 2000 to 2016. So you can see, if you just look at the visualization on the left side, it gives you an impression that these wins, like the team is more or less winning the same number of matches every year from 2000 to 2016. Now this is happening because they are not using the proper scales. They are not using the proper scales on the y-axis. So you can see on the left graph, on the y-axis, they have 0, 25, 50, 75, 100. Even though they haven't won in any year, they haven't won more than 25 matches, they're using a kind of scaling in that particular way, 0, 25, 50, which is making it look like they have almost won more or less the same number of matches every year. But that's not the actual case. Now if the scales are adjusted properly, on the right side you can see that the number of matches that they are winning is varying quite a lot. So in 2004 and 5 they have won less matches. In 2010 and 11 it is increased, it almost doubled during 2010-11 compared to 2004 and 5. Now all of this insights or the information in the data is not captured properly when they are not using the proper scales, which is on the left side, right? So using proper scales is very important in order to create good visualizations. And also, not just the scales, we need to use proper labeling. The labeling should be very clear. So you can see on the left side, even though both of them represent the same data and have the same labels, it is more easier to read the visualization on the right side, to understand it, because the labeling is very clear in that particular visualization, right? So this is another example, and this is one more example for you. You can see that on the left side, so both of them are pie charts, both the visualizations, and on the left side you can see that the percentages are written within this pie chart. Now the problem here with this specific pie chart is that we are already using thick colors to represent the pie chart, and on top of it we are doing a labeling with again a dark black color. So which makes it a little more annoying to read, or you can't clearly see the percentages. So that is why you can see that on the right side what we have done is, like, we have written the particular labels, that percentages 31, 12, 24 outside that particular pie chart. So that is the right side visualization. Now I'm not saying that all the time the visualization on the right side, the pie chart should always be in that particular way. Now in this context, this is just an example of how we have to try to make these labels as clear as possible. Now there are multiple ways. They might have used some different color combinations as well in which they can make the labels clear, but the essence here is that the labeling should be as clear as possible. So compared to the left one, clearly the right visualization, in the right visualization, the labeling is much more clearer. So now another example is where we might do incorrect labeling, which is again creating a kind of a lie factor, and it might also even confuse the audience who are looking at the graph. Now this is an example of one such. So you can see that there are these bars, different bars, indicating some data of medical assistants, and then you can see that the graph, the first bar is 337,690, but then the y-axis is not labeled correctly. It has incorrect labeling, and it shows it's just 35,000 around that particular point. So now someone who looks at it is confused whether it is actually 35,000 and whether the numbers on the bar are wrong or incorrect, or whether the labeling is incorrect and the numbers are correct. Now that is creating a kind of a confusion, and this is outright misinformation, or it is creating a kind of a lie factor in the graph too, in a way. So the labeling should always be correct. That's the fundamental thing. So it should always be correct, and along with being correct, the labels should be very clear, and the scales should also be proper when we represent the some kind of data. So these are different kinds of principles of data visualization based on which we can say a particular visualization is good or bad. So let's just quickly summarize them.